The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone, and welcome to today's webinar, Commercial Solar Peaker Batteries Part 2. My name is Andrew, and I'll be moderating this morning. Our series today is going to last from 11 a.m. to 2:15 p.m. Central Daylight Time, and there will be a 15-minute break in the middle. Before we begin here, there are a few things I just want to remind you about. Remember, it's very important to please be logged into the webinar through your own connection. We do require this so that in the event that Half Moon Education or you are audited by any licensing board, we are able to accurately prove your attendance. Also, it will be the only way for you to gain access to the quiz at the end of the program, which is a requirement if you're trying to obtain continuing education credits. Next, to the right of your screen, you'll see a panel. Toward the bottom of that panel, you'll see a dark gray questions bar. If you double click that, it will open and allow you to submit questions you may have during the webinar. Also, if you click and drag a corner of that box, you can make it larger and easier to use. If you happen to lose sound through your computer speakers, please see the audio tab on the panel. You have the option to dial in with your telephone. For any other issues you might have, please call Half Moon at 715-835-5900. With that, I'd like to introduce our speaker. I know a lot of you were here the other day. Mr. John Ross Cromer, Master Electrician, Mechanical Engineering degree from the University of Pennsylvania. He's also the author of a new book, Solar Power Design and Development, An Introduction to Rooftop Solar. He brings 10 years of solar project experience, including residential, commercial, and small utility scale projects to his work. Please welcome Mr. John Ross Cromer.
All right. Hi, everyone. Welcome back. I want to start off with this chart that we kind of skipped over yesterday. What we're looking at here is, it's called a cycle chart or a depth of discharge chart. And it's pretty common for lead acid batteries to provide this kind of chart on their spec sheet. And so what we're looking at is actually three different kinds of lead acid batteries. And the bottom line here is what is commonly marketed as a renewable flooded lead acid battery. And the next line up is often what is marketed as a premium flooded lead acid battery. And then up at the top, this orange line is where the industrial flooded lead acid battery comes out to be. And then up here in green is, and this is not a chart that Tesla provides, but this is a more elastic, low-end lithium ion. And so if we went and charted, lithium iron phosphate batteries, what we would probably see is something that looks very similar to Tesla's, but it's just rated for, even larger cycles. This kind of chart is not very necessary on a lithium ion battery because it is an elastic battery. And so there's a kind of a direct relationship where, if you're rated for, say, 3,500 cycles at an 80% depth of discharge, you're going to be getting, twice as many cycles at a 40% depth of discharge. So no matter, if you use your battery half as much, you'll get twice as much life. That's not the same as a lead acid battery, where you're going to get much more elastic range up at the top of the battery and a more damaging inelastic range at the bottom of the battery. Let me just do a real quick online search for a battery spec sheet here. Let's go with a Trojan lead acid battery spec. We got percent of capacity, so let's see. We don't have it on that one. let's try a different data sheet. So sometimes these don't come up on every single data sheet, but here we go. Here's this same chart, but kind of zoomed in for this particular lead acid battery, which is let's see what we're looking at. It's being marketed as a solar deep cycle flooded lead acid battery, and it looks like it comes with a watering kit, so it's a unsealed flooded lead acid. And so in the lead acid arena, you have to figure out, okay, well, how many cycles, what's the life I'm going to get out of my battery? And so you go through your usage and you determine based on your battery bank size, what is my average depth of discharge? And so if I'm often in the off-grid market, we'll design a battery to take the house 2 or 3 days off-grid, and so its average usage is not going to be, at the day 3 mark is when you get down here. So on a typical day, you only get to maybe a 25 to 30% depth of discharge. And so you can say, okay, well, based on my battery size and on this technology, if I'm at a 30% average depth of discharge, I can expect about 2,000, maybe 2,100 cycles. And so we'd say, okay, well, that's a daily cycle. So, 2,100 divided by 365 days, our battery bank's going to last 5.7 years. So this chart was kind of necessary for calculating the battery life of lead acid, mainly because you have this kind of major inflection point where it goes from its elastic range into a range where if the battery is regularly operating down here, it experiences more of that barnacle creation on the anode. It experiences more degradation. And so what we can see here is that if we have an average daily discharge of 80%, we're going to get maybe 700 cycles. Whereas if we have an average depth of discharge of 40%, we get over 1,500 cycles, so more than twice the battery life. And that, so what I'm saying is, in the lead acid arena, we had to have these kinds of charts because there's a definitive range on when you get more into this inelastic region, you start getting less life out of the battery. On these kinds of charts, the inflection point, say for a non-premium battery, occurs further up so that you can't deep cycle the battery on a daily basis of more than 20 to 30% of the battery. Whereas industrial flooded lead acid, the inflection point occurs closer to the 50 to maybe 60% range. So let's go back to this slide. So what I've done here is combined these cycle charts and then took Tesla's warranty, which is that's why Tesla is providing a kilowatt hour warranty, where they say our battery is warranted for 37,800 kilowatt hours of output, regardless of how you cycle the battery. If you cycle it down to 80%, you'll get 3,500 cycles. You cycle it down to 40%, you'll get 7,000 cycles. It's a more it's a smoother relationship. And what I found that was kind of surprising was this red line is kind of where we were looking at the Trojan battery previously, or maybe this blue line, is between a renewable battery or a premium renewable battery. And forklift batteries are way up here. And so that kind of surprised me that industrial flooded lead acid batteries, the same kind of batteries that are used on forklifts, actually are kind of halfway in between the performance of what most solar installers in the battery arena would know as a lead acid battery and lithium ion. And then like a golf cart battery or a car battery would be kind of way further down this scale. And so we were briefly talking about the concept of combining multiple battery chemistries together. And even though Tesla is buying lithium ion at $130 a kilowatt hour, you're as a small orderer just for the battery or cell, you're going to be paying much more than that. We look at Tesla's advertised price of about $8,000 for the Tesla Powerwall, and it's a 13.5 kilowatt hour battery. And yes, you're buying the not just the battery, but also the inverter hardware that goes on with it. But it's kind of, you can't buy one without the other as far as Tesla's product is concerned. And so by the time the lithium ion battery gets to the consumer market, you look at, $8,000, let's just attribute maybe $2,000 to the hardware. You're looking at for your low-end lithium ion around $450 just for the battery itself. Whereas the industrial flooded lead acid new starts at around, or not starts, is around $200 a kilowatt hour, or half the cost, over half the cost. And even recently, on my most recent off-grid project, we went with a refurbished flooded lead acid battery, mainly because we were constrained by budget, and so we had to do everything we can to cut cost. We went with a refurbished flooded lead acid at $90 a kilowatt hour. And so where the concept of an energy server, and not that there's a lot of companies doing this today, is saying, well, maybe we could blend some battery technologies and maybe use industrial flooded lead acid as our base, and then go with lithium ion, or even a higher end lithium ion that costs more than $450 a kilowatt hour for our heavy demand, heavy usage. So we started to talk about DC and AC coupling architecture yesterday, and for the most part, you're going to be doing AC coupling on these commercial systems, with the battery being on its own inverter with its own control software. You don't have to do it that way. I would say for like rooftop projects, you probably are, and then maybe if you're buying for utility scale, you may end up having a skid, like we saw with the Delta system, where they do have higher voltage charge controllers going into it. One company that kind of springs to mind for me is a company called Amped. And so what AMP does on the commercial and industrial level is the same thing that SolarEdge does at the residential and commercial level, but instead of putting a optimizer or voltage regulator behind every single panel, Amped puts one behind every circuit, actually every couple of circuits. And so what these voltage regulators do is supply, they take the array output power, which is a variable voltage. The voltage jumps up and down much more quickly than the amperage does, and they control it. So for the most part, unless the array is turning off completely from cloud coverage passing through, they kind of turn it on end and they fix the output voltage from the array and vary the amperage rather than the other way around. And so what we see here are voltage regulators for commercial and industrial systems that can supply a fixed voltage output starting at 600 volts, but going all the way up to 1500 volts. And so if you're installing a higher voltage lithium ion battery, there are products out there to deliver a constant regulated voltage from your solar array to the battery on the DC side. So, it's not that DC coupling is impossible on commercial battery banks. It's just that there's more the way it's perhaps more simple to have the solar array on its own inverter and the battery bank on its own inverter. Because companies like Tesla are interested in not just selling you the battery, but also the electronics behind it. Let me get back to our slide here. Okay, so we talked a little bit about AC and DC coupling. For a variety of reasons, AC coupling seems to be the more preferred configuration for larger scale projects. A lot of that just has to do with the availability of products on the market today. Or if you're expanding an existing array, like if you already have a solar array and you want to add batteries to it, there's really little reason to throw out the old infrastructure, just have an AC coupled system. Also, technically, if you're using all of the power from the solar array, what that means is it's either going into the load or being sold back to the grid. So if you're using 100% of the power from the solar array, then AC coupling is technically a little bit more efficient because the energy is not flowing through the battery. It's just going directly into the load. On the other hand, if you're in like an off-grid situation where you're primarily running off the battery, then it's a little bit more efficient to just feed the solar directly into the battery and not have it be removed, involving the number of processes that it has to go through for getting the energy into its final point of use. But getting too caught up into the nuanced discussion between AC and DC coupling is kind of silly. Technically DC coupling should be cheaper, but the lack of product availability on those high voltage DC charge controllers, it makes it really kind of a wash from a cost perspective. So, maybe down the road into the future, we'll see DC coupling become more popular. But right now, AC coupling is the more popular route to take. Likewise with DC coupling, DC coupling is a little bit easier for off-grid because our inverters have protections in them that say that just a basic dumb solar inverter without any batteries, it needs to see a grid signal in order for it to turn on and function. Almost like an electric start generator needs to have a battery inside of it to crank, even though it's a generator. Your solar inverters that don't have batteries in them need to see an external power source to turn on and function. Whereas the charge controllers that are directly tied to the battery bank will just turn on naturally. And that means in an off-grid setting, a system can black start, a system can start itself up under a DC coupled configuration where it can't do that under an AC coupled, but there's solutions for that. One solution is to have the battery inverter not fully discharge the battery, but to hold on to a reserve capacity so that in the morning it can start the solar array back up. Another solution is simply to add a generator so that when the battery voltage gets low, the generator turns on and either can function in tandem with the solar array or charge the batteries up, or wait until the sun comes back up and provide the grid signal for the solar array to turn on. Let's looking at some line diagrams, because we have plenty of time in today's program. This is kind of a standard wiring configuration for a DC coupled system, where you have your solar array going into landing on a charge controller. You'll need a disconnect switch between the two. Then from your charge controller, we're landing on a distribution panel. This distribution panel made by Schneider is a little confusing because there's actually a DC side to it and then a separate AC side to it. So, often when you go for a manufacturer provided solution, they're selling you specialty distribution panels that cost a lot more money than your distribution panel at Lowe's or Home Depot does, or from your electric supply store. You don't necessarily need a specialty distribution panel, but it does, make it look nice and neat and take up less space. Do we have let's look inside one of these distribution panels. We'll look at a wiring diagram. And I selected this one because it's complicated. What we have is a single battery bank, two charge controllers that are DC coupled to the battery bank, what's called a double stacked inverter. So here's inverter 1 and here's inverter 2. And that can be kind of nice in the off-grid arena to have double stacked inverters, because if something goes wrong with one of them, the other one can function while the first one is offline. You can't double stack inverters willy-nilly. What you have between these two double stacked inverters is an Ethernet port and a communication box that kind of governs the relationship between the two inverters. One inverter being what's called a master inverter, and the other inverter being a slave inverter. Now, just a finer detail. If one inverter fails on you, if your master inverter fails on you, the slave inverter doesn't automatically turn into the master inverter. That might be something that more complex programming, such as the energy server, would do. But out of the box, generally, if something goes wrong with your system, the inverter company wants you to actually come out and take a look at it to see what's going on. So even in a double stacked inverter configuration, you don't have a completely seamless transition. So looking at these wire lines, we have a shared DC bus that our charge controllers are landing on. So here's our solar array landing on and feeding into our charge controller, and our charge controller coming back. Then we have our DC bus that the battery is on. That then goes into our inverter. So it can be a little bit confusing, but we have to remember that our solar array is going all the way up to 600 volts in a commercial setting. In a utility scale setting, they can go up to 1,000 volts or even higher. And then we have to regulate that voltage via our charge controller. And so our charge controller is taking the variable voltage from the array, fixing its output, and bringing it down to the voltage of our battery bank, which in the lead acid arena may be 48 to 60 volts, although they can go higher. There's really no reason that a battery bank can't go higher. So, the thing about forklift batteries is that they're very low voltage and very high amperage. And so presumably on a commercial array, you could get away with doing a series of forklift batteries to get them into the same voltage as a lithium ion battery bank. Although you would have to then go in and program the lithium ion battery inverter to not discharge the batteries over greater than maybe a 25% discharge rating, so that they're not discharging in a 2-hour time frame, that you use software controls to set the maximum output. Say, hey, the forklift companies say, our batteries we're quoting you at around a 6-hour discharge cycle. So then your inverter is sized to the voltage of the battery bank as well. And so a lot of residential off-grid inverters are 48 volts, although the Solar Edge inverters, based on the higher voltage lithium ion batteries, are more around a 380 volt nominal. And so we're taking that battery voltage and then connecting it to the AC side through our inverter. So we're coming in through the DC side and then going out through the AC side and landing on our AC service panel. What's pictured here is the AC service panel that can be fed by the inverters or by a backup generator. We have two service panels here. One's coming in from the grid, and so we're feeding the bottom with here's our generator feed, and then this generator feed is coming up and going through the inverter and back out again into the service panel bus bar. So your generator and your inverters generally have to be the same size. If you're going to air it depends. If your generator is flowing through your inverter, then your inverter needs to be the same size as the generator. Otherwise, if that generator power tries to land on these bus bar terminals, they may overheat and burn up the terminals. If your generator is undersized compared to the output of the inverter capacity, you should be okay. Although an undersized inverter has to run longer. So, that's a common installation error that I see in battery-based systems, is they go and they buy a 2 kilowatt battery inverter and a 15 kilowatt generator. what you would do in that circumstance is not use the automatic generator controls that come with the battery inverter, and instead put the generator on a kind of an auto lock switch that either locks out the inverter breaker or locks out the generator breaker, and just do it either on an automatic transfer or a manual transfer. Manual transfer switches are pretty cheap. And so in this Schneider system, we're feeding both a what would be the main service panel to the building, and then additionally protecting a critical load panel. And so that's kind of something you can consider when you're planning even a commercial project, is to say, well, hey, if we want to take advantage of the backup capabilities of our battery system, that will involve rewiring a panel into a critical load panel separate from your main service panel. Otherwise, you have to do a system that is capable of supplying the entire building. And at that point, you can land it between the grid and your service panel. So that's actually part of National Electric Code, that the backup system has to be capable of supplying the loads on the backup panel. So you can't just put a 200 amp service panel and supply it with a 1 kilowatt backup generator. And that's furthermore, that's why at the residential level, you see your battery inverters commonly having a critical load panel outlet built into them to feed a very small, maybe a 2 kilowatt critical load panel. Like, oh man, that stinks, because if I lose power during a blackout, I want to power my entire building and not just a critical load panel. Code says your backup system has to be able to supply the loads that it's trying to power. So that means you have to actually do a building level backup system to supply building level backup power. So if you have a 1 megawatt facility and you're only doing a 100 kilowatt commercial solar peaker, you're still going to have that critical load panel and not be able to supply the entire building during that blackout. You would have to have a 1 megawatt output to supply the entire building. And that's a good safety measure too, because you don't want, at the residential level, you don't want your deep freeze not to work because your kid's playing Xbox in the middle of a hurricane. At a hospital, you want to be able to protect your emergency power and keep that on a separately managed than the non-critical devices. Well, we've talked about this enough. This is just saying that they now make, even at the commercial level, little rooftop inverters to meet de-energize. Right now, National Electric Code says you have to de-energize outside the perimeter of the array during a blackout. During a grid failure. Well, I don't know if that's. It doesn't have to de-energize. It needs the capability to de-energize. So in a dumb system where you're just backfeeding onto the grid and there's a grid failure, it needs to de-energize. That doesn't mean you can't be supplying a critical load, but the fire department still needs to be able to have some means to de-energize the system if there is an actual emergency going on with the solar array at the building level. And so the rapid shutdown requirements now state that you have to de-energize the array outside of the array perimeter. While we're talking about it, I wanted to show you some pictures of how these commercial rooftops arrays are attached to membrane roof systems. This is a TPO roof. And so, on this particular roof, it's not perfectly flat. It's an old warehouse that didn't originally have a TPO roof. The TPO roof got put onto it years later. This building was actually owned by the city and then sold when the maintenance on the building got to be too expensive. And so, you're already starting off with kind of a rickety building. And so what I say all that to say, whenever it rains, this building gets standing water on the rooftop. And so the last thing you want to do is poke a hole in the roof and cause a leak. Well, there's actually some more issues with that. The alternate, other than positively attaching into the rooftop, is to weight the system down with concrete. But the problem with these concrete systems is twofold. One, they usually only sit an inch or two off of the roof deck. And so if you're getting pooling water on your rooftop and you get an inch or so of water, you can start getting kind of a low profile solar array sitting in water. On top of that, they're going to fill in these ballast pans with concrete blocks, which is a carryover from the satellite mounting industry. Now let's go put a small satellite dish on the roof, and let's just weight it down with a couple concrete blocks so it doesn't blow over. Okay. Well, now these solar concrete ballast systems are filling up the entire roof area with loose concrete blocks, which, code is very concerned with rapid shutdown and de-energizing the array during a fire. I wish they would pay more attention to having the roof covered with loose concrete blocks during a fire, because if the array is burning a hole in the roof, some of these old school solar arrays, and this problem has since been fixed, but in the early 2000s, mid 2000s, your large commercial solar inverters would be negatively grounded, and it would create a blind spot in the ground fault detection system. And what would happen is you got aluminum conduit on some systems. I like going into the roof with my home run cables, but if you're running your conduit across the roof, as is common, often you'll get copper cable inside aluminum conduit at the hottest part of the building. And so what was happening is, in the early era of commercial solar, installers were running very long aluminum raceways with copper conduit on the hottest part of the rooftop and not putting in any expansion joints or service loops in their runs. And so by the time you get to the combiner box on this, where all this conduit would come in together, that conduit would start pulling out of the box, and then you get a conduit busted off, and now all of a sudden one of those cables can start fraying and ground faulting, and under the right circumstance, it wouldn't be detected by the commercial inverter ground fault protection system because of this blind spot issue, which has since been solved. We do floating solar arrays that are not positively or negatively grounded. Instead, they're functionally grounded. So all the metal parts are still grounded. We're just not connecting the negative pole of the inverter directly to ground anymore, fusing both ends. But in this one particular circumstance, it was causing commercial solar arrays where you'd have multiple circuits wired together. They would start feeding into the ground faulting circuit, which is only sized for one circuit's worth of power, not 20 circuits worth of power. And it's causing these commercial rooftop solar systems to burn the building up. There's a warehouse fire called the Dietz-Watson fire in New Jersey. And on the news, they said the fire department showed up, but then saw concrete blocks falling through the roof of the building, so they couldn't go inside the building to put the fire out. They let the whole building burn down. Now, these concrete ballasted systems can weigh over 6 pounds a square foot. Some can get up more than that. And a real easy way to remove the concrete is to positively attach to the rooftop. Well, the solar installer doesn't know anything about roofing. We think pools of water on the rooftop, and if we poke a hole in there, that's the last thing a solar installer who knows nothing about roofing wants to do. But the way, say, on a TPO roof it works is you put in your U-bolt around your rafter, and kind of screw in your faceplate, and then put in additional attachments to kind of tamp down the TPO roof around it. And then you have a flash pad that goes over the attachment, and then it just gets melted onto the TPO roof with kind of a souped up hair dryer. So it gets, they call it welding. You're not taking a big butane flame and torching it. You're kind of melting the flash pad onto the TPO roof. Something that a commercial roofer does all the time for flashing everything else on a TPO roof. And so by positively attaching to the rooftop, and in our case, we went with a racking system that also elevated the array off of the roof deck. You don't need to do that. If you use a concrete ballasted system, you can positively attach select points in order to reduce the weight requirement and get this stuff down to about 3 pounds a square foot. So I guess what I'm trying to say is poking a hole in a flat roof is not the worst thing that can happen. I greatly prefer positively attached systems in high seismic zones. They're also important because of, again, loose concrete bouncing around on a roof in an earthquake is not a good idea. Now, this is a different kind of system called Grid Assist. And I thought I'd mention it because it does have some commercial applications. I use Grid Assist in residential battery systems when we're facing punitive interconnection charges. So in my region, if you interconnect a solar array to the grid, not only do they only pay avoided cost for the outflow, but they'll also increase your fixed fees. The most egregious co-op that I know of actually charges you, they pay you avoided cost, but then they take a penny off of that as a wheeling and distribution fee. And then they increase your fixed fee by $15. And it's the revenue equivalent as you have to outflow 8 kilowatts worth of power onto the grid in order to make up for the additional charges that they bill you per month. And so in the residential circumstance, you can have this case where maybe you don't want to outflow because you don't want a parallel operating system that operates parallel to the grid and supplies the load or backfeeds to the grid. Maybe you want a system that is disconnected from the grid and any surplus power goes into the battery or the load, and maybe you generate a little bit too much energy and some of the energy gets stranded and not used, but that's better than facing those interconnection fees. And so I'll do this on residential systems in the TVA, and for the most part, the customers are all right with that because most customers do want batteries and they do want the ability to have that backup power protection, especially when you're dealing with longer term paybacks. Having these less quantified values is important. At the commercial level, where a grid assist configuration is important is if you're protecting sensitive electronics from, say, power surges. Let's say, hey, if lightning strikes the grid and sends a power surge up the power line, depending on your business application, you may be protecting your system with, uninterruptible power supplies, battery backups, and every time they get hit with a power surge, you may need to replace them. So just this morning, I was on the phone with a customer who says, and they do media production, and so they have server rack after server rack of digital media files, which they need to store for their clients. And so he says, I'm just tired of replacing my UPS systems. Can I just have some of my building be off-grid and the other part of my building be grid-connected? So, that's kind of straying away from the commercial solar peaker discussion. But I just thought I'd mention that, yeah, there is a design configuration called Grid Assist, where for the most part, you have a solar array and a battery. This shows a AC coupled system, although it can be a DC coupled system with the grid going into the battery inverter as well before going into the load. This is an AC coupled system, but either way, under a grid assist configuration, you're primarily running off grid with your solar array and your battery, but then you can connect the grid only to recharge the battery. So that it's almost I call it a one-way system where you're no longer, and there's ways to do grid assist where you can also outflow onto the grid, although it's kind of self-defeating. Maybe if you're doing a whole building off-grid system, you may want to outflow when you can, but then also have the ability to disconnect. So, a lot of this stuff you can do in a variety of configurations. But I just thought I'd mention it, that there are systems that are just one way, where you put a battery in between the grid and the load, and that the inverter only flows into the load and not out to the grid, so that the grid might land on the input on the battery inverter, and then the output of the battery inverter goes into the load, so that you can isolate the load's electronics from the grid for a variety of reasons, whether you're trying to, in an ironclad way, protect those electronics from up the power line power surges, or if you're trying to circumvent punitive grid-tied policy. There's solutions for that. So this is a more of an off-grid discussion. I think I want to talk more about something that's not illustrated here. So what I'm saying with these two slides is you have to look out for charge controllers, because many of the charge controllers that are available are at much lower voltages than what solar installers are used to. And so you don't want to do 150 volt charge controllers on a commercial building, because 150 volts on a solar array only gets you to about 3 modules before you get to the end of your circuit. So even at the residential level, I'm looking at higher voltage charge controllers, and there aren't many. Schneider makes one, Morningstar makes one, to get up to 600 volt circuits. And then we saw that Amped makes 1000 volt module level panel electronics for the commercial arena. You know, what I really want to talk about here is a commercial wiring technique that I'm a fan of. I would only recommend it to seasoned installers. It's not something you want to start out a new crew with. But commercial solar modules are a little bit taller than residential solar modules. So we call them 72 cell modules instead of 60 cell modules. And that is simply because on your solar cells, a 60 cell module is 6 across and 10 down. A 72 cell module is 6 across and then 12 down. 6 times 12 is 72. A 72 cell module is simply 12 more cells added onto the bottom of the module. So it's a slightly taller module, about 6 feet tall instead of 5 1/3 feet tall. And the reason that's important is because these module whips that come out the back of the module, normally they just plug right into their next door neighbor. But the module whips are also sized for not just a portrait configuration. Now you see all this extra slack here. Now that's because these module whips are also designed to be able to plug in a landscape configuration as well. And so if you install in portrait instead of landscape, you're going to get a bunch of slack. So the reason why I mention that is if you have a slightly taller solar panel, you have a slightly longer module whip. And so what installers have discovered is that instead of having all this extra slack, what you can do with your module whips when you use 72 cell modules is not plug into your next door neighbor, but go all the way across into the adjacent module and go every other and then you get to the end and you come back. You know, that was our positive run. Now we're coming back with our negative run and doing every other again. So it's called skip stepping. It's called leapfrogging. And what's interesting about that is under a normal circumstance, you get to the end of your circuit and you make a crimp and you have a home run circuit going down the end. But if you skip step and you go every other and then you come back every other, instead of your circuits starting at one end of the row and ending at the opposite end of the row, If you skip step, both your positive and negative circuit end up and start at the same spot. And so, there's one advantage of that is you gain the efficiency of getting rid of that dimension of your home run circuit. That's not a very big gain, nothing more than a solar installer could appreciate. But the other thing that's nice about it is you get rid of all this extra slack, which is a little bit difficult to cable manage up on the roof. It just kind of hangs out the side back of the module, it adds extra weight to the module. So it's a little bit difficult to manage that slack. So, one advantage of 72 cell modules under the right kind of racking situation is you can use skip stepping or leapfrogging and have your circuits kind of start and stop at the end of the same place. And that's where, a really good solar designer is incorporating all of that into the array layout to make the module circuits lay out in the most straightforward and logical manner possible to assist the installation and maintenance, so that you don't have to go hunting where all of these circuits are starting and stopping up on the rooftop. So let's take a sidestep for a moment and talk about commercial solar financing. Financing is available for commercial solar projects, just like it's available for residential projects. There are companies that specialize in solar commercial financing, just like they do residential. What I'd like you to think about is community solar as a mechanism for project financing. Maybe not the upfront capital for the project, but more as the long-term off-taker of the project. There's a few reasons why community solar makes a lot of sense to be the end user of the solar array, the ultimate investor of the solar array. Mainly because community solar participants are, if I wanted to paint them in a negative light, I'd say they're chumps. And the reason I say that so negatively has to do with what community solar is replacing, which are voluntary green energy plans. So if community solar participants are chumps, then voluntary buyers of green energy are even worse. Most of them are doing it for altruistic reasons. And I think that is being taken advantage of. The reason being, the average green premium price is well above the average green premium cost to the utility. So what we're talking about is kind of the same thing as cap and trade, but at a voluntary level. And so if you don't have a mandatory cap and trade system, or what is more common is that the state does have some form of a mandatory cap and trade system, it's just so easy for the utility to achieve that you end up with a surplus of, they call them RECs, which stands for Renewable Energy Credit. It's kind of the same thing as a carbon credit, but the Poindexters will say a carbon credit is equal to 1 ton of CO2 offset, whereas a renewable energy credit represents all the green attributes associated with a kilowatt hour, or more traditionally, a megawatt hour of green power generation. And so in these renewable portfolio mandates by the State Public Utility Commission, they say, okay, we want X amount of green generation, and if you don't do any green generation, but that wind farm does 100% green, and our mandate is for 5% green, then the wind farm can sell 95% of its renewable energy credits to the coal power plant. And so the coal power plant, buys the green credits and suddenly becomes green. And through this, for lack of a better term, cap and trade system, they meet their state green energy mandates. And usually it's like a limbo contest where the limbo bar is set 10 feet up in the air and everyone can just ride a horse underneath it. And so you end up with this surplus of green energy credits on the market. You end up with a market where the green energy credits are nearly worthless. And so the utility will buy these green credits and then go repackage them as a voluntary green energy plan. And often the markup can be egregious. And so most customers are willing to spend a premium for green energy. And that premium, most customers are willing to spend, a penny a kilowatt hour. They're willing to increase their price of energy in order to buy green energy instead of brown energy. And I think that is, looking at the cost versus price difference, I would call it a scam, because you get an altruistic do-gooder spending $1 on voluntary green energy contributions, and out of that dollar, only 5 cents makes its way to the green power project. Where does the other 95 cents end up? It just ends up in the overhead and administrative cost of the power company. So in other words, these environmental do-gooders are paying the power company for doing environmental remediation that the power company should otherwise be doing to begin with. So, I don't think that this is the best product on the market for cleaning up the environment. And community solar is replacing that. And there's a lot of reasons for that. One is, instead of being associated with some wind farm that's thousands of miles away, that community solar project can be identified, saying, I'm participating in that project that's located 20 miles down the road, and I'm a stakeholder of some sort in helping that project come out of the ground. What's interesting about that attitude is it says, well, most community solar participants are not financially motivated. Saving money on their electric bill is not their primary motivation for participating in community solar. In fact, almost all community solar programs do not save the participant any money at all. Just like voluntary green energy plans don't reduce your electric bill, they increase your electric bill. Most community solar plans don't reduce your electric bill, they increase your electric bill. And yet the same kind of person that would participate in voluntary green power purchasing is the same kind of person that participates in community solar. It's because they want the power industry to do better in terms of its emissions. And so they're willing to spend a little bit more voluntarily in order to help the power company do exactly that. So here's an example of a community solar project. So Geronimo Energy has sold a portfolio of community solar projects to Berkshire Hathaway. The portfolio includes 66 megawatts of solar projects across 21 locations in 16 counties. Oh, okay. I after not having any success, I think I removed those slides from this program. But the long story short, I contacted Berkshire Hathaway Renewables and Geronimo Energy to find out more about the terms and conditions of the project, and they flat out refused to share them with me. On multiple levels of the company, sent me emails to tell me they would not be telling me anything because I'm not actually a customer of Minnesota Electricity, and out of concerns for customer privacy, they would not tell me anything about their program. So I found a participant in the program who would tell me about his terms and conditions. And he says, well, look, it's a 25-year agreement. There's a clause for terminating the agreement if you move out of the service area or if you lose your house or if you die, but otherwise, there's an early termination fee. And that they say they're going to work with you to try and find a participant to replace your participation in that. And so what we'll find out is, there probably won't be too many early termination fees associated with this stuff because the savings in the participation don't come till the very end of the term. So the contracts get increasingly better as the term goes along. The flip side of that is they start out not very good. But what we find out is that's not very important to the customer. As we say, he says, it's a little bit of a gamble. I may save $10,000 over the course of 25 years, or I may end up just paying a little bit extra to offset my energy usage. Well, I think there's a pretty big difference between paying a little bit extra every single month for 25 years versus saving $10,000. And hey, the participant agrees with me. So I say, well, tell me a little bit more. What he's basically doing is trading up or hedging his power bill. He's saying, let me increase my electric bill today, but fix the rate for 25 years. So I have a 25-year contract that's going to define what my electric rate is going to be for the next 25 years. So I know, I'm not going to get a letter in the mail that says, hey, your electric rate's going up by 10% this year because we messed up and need more money and you're our customer, so you need to give us more money. He's getting a 25-year contract where the rate is stabilized. It's not necessarily flat. What's common in these terms is for your rate to go up by 10 to 20% and then to increase by 2 to 3% a year. That's actually an advantage to the power company. If I'm a power executive and I find out that I can get one of my customers to voluntarily increase their electric bill by 10 to 20% and commit to a rate escalator for the next 25 years, I'm going to say, sell that guy some electricity. That's great. I might be deregulated in the future, and having all these contractors locked up or customers locked up in these 25-year agreements might eventually save my hide when the deregulating group comes to my door. I say, well, how much is the rate stabilization and incentive for the participation? And he's like, well, it's not really much. Even if I'm paying a little bit more with solar, what I'm looking for, and I thought this was really interesting, he's looking for a source that's more local than what the voluntary green power pricing was. And what he's looking at is saying, hey, I can't afford to or put solar on my roof one way or the other, but what I can do is spend a little bit more money to see a local project come out of the ground and feel like I'm helping out in the solar industry when otherwise I couldn't participate in it. And so you might be scratching your head and saying, well, why would anyone just increase their electric bill? If you're that person, you're probably not the person who's voluntarily buying green energy already. But voluntary green energy purchases are not an unsubstantial amount of total electricity sales. Even before the solar revolution, these green energy plan purchasers reflect about 2% of utility revenue. I said, how much? Well, here's a different program. So in the Minnesota program, you essentially increase your electric bill by 10 to 20% and then have a stabilized rate for the next 25 years. Here's a different community solar program where the participants actually do save money right off the bat. So there's a community solar program in Massachusetts where you pick up the phone, you call the company and say, hey, I want to sign up for the community solar program, and immediately they will lower your electric bill by 5 to 10%. Hey, that's a great deal. Now we're talking. Now, I didn't like the community solar program that increases my electric bill, but I can get excited about a community solar program where I don't have to do anything and I lower my electric bill. I'd love to do that. Why should you join? Well, you get that experience of solar participation at zero cost and you immediately start saving money out of thin air. That's a strong sales pitch. All right, so there's no such thing as a free lunch. So how does that program actually work? Well, the thing is, in Massachusetts, they subsidize the heck out of the solar industry. In Massachusetts, their renewable energy credit program, their state-level cap and trade program, values solar renewable energy credits at 2 to 3 times above the retail price of electricity. So the carbon credit that the solar array produces is worth far more than the value of the electricity itself. And so if I can give someone a discount of 5 to 10% off their electric bill, but that allows me to go to the state regulator and say, I have 100 participants in this community solar program, so please accept my utility scale permit for a solar farm so that I can go and participate in this SREC market. Please, I have the participants already, so please greenlight my project. And that's kind of how the community solar programs, whether or not they are increasing the customer's electric bill or decreasing the customer's electric bill, that's kind of how they work. Is there's a marketing effort to sign up customers for the program, and if your project is not already out of the ground, that contact list of participants is important to show that you have sufficient public interest for the grid operator or regulator to approve your project. And so the thing about solar in Massachusetts is if you were to buy it and put it on your rooftop and participate in this rec market on your own, you would get a very favorable payback, a 4-year payback, a 5-year payback, something that in normal circumstances would be too good to be true, save for this subsidy program. And so someone who can't put solar on their rooftop, but will commit to buying electricity over a 25-year rate, as long as it comes from a solar farm, can get cut in on the deal a little bit by the developer. So, I don't think that is a sustainable business model. If we go to 100% renewable grid, carbon credits will be worthless. So obviously, under a circumstance that embraces renewable energy growth, it's not a sustainable business model. These are developers going after the short-term opportunity, for better or worse. So there's actually an interesting website called SREC Trade where you can go to, and they function as a renewable energy credit broker. And as we can tell from SREC Trade, there aren't too many markets where these solar renewable energy credits have a lot of value. Massachusetts and New Jersey are kind of the main ones. So if we want to check the spot prices of Massachusetts renewable energy credits, they're still going for 32 to 40 cents per kilowatt hour. Okay, so in the Minnesota model, you're basically a power customer who's signing up for a rate structure that locks you into a rate above your current rate for 25 years. And, if the price of electricity increases faster than that locked-in rate, you'll end up saving money. Odds are it's not going to increase faster. It's very rare for the price of electricity in the United States to increase above the cost of inflation. Not that it can't happen, not that it hasn't happened in certain regions, but, and maybe there's some argument to say we're long overdue for rate increases. Maybe there's the no such thing as a free lunch argument applies to the dumping of carbon emissions. That's kind of a debate for this time and place. In the Massachusetts model, they're locking themselves into a rate for 25 years, but because of the regional subsidies being so large, they're being cut in on the deal, and they're lowering their rate right out of the gate. There's always the risk that they're locking themselves into a rate that's 5 to 10% below retail, but maybe the retail price of electricity goes down, and they're still committed to this long-term program, so they end up losing money. But I don't think that that'll happen either. In some ways, the price of electricity is going down because of renewables, but we're shifting that cost onto the taxpayer through federal tax credits for solar. So, the renewable energy being added to the grid today is not increasing the price of electricity, but the federal government's making 30% less revenue via the 30% tax credit. So it's kind of pushing money around. Is there a community solar program where it's not based around rates, but it's more like traditional owning a solar array where you just buy into the project and you get a credit for 20 years, just like if you bought into the solar array and on your roof and you get savings off your electric bill? Is it all just rate structures? Well, it's kind of like the difference between taking a lump sum payment or an annuity. There's all it takes is a different kind of financial structuring to do it one way or the other. And so in Michigan, there's a community solar program that kind of gives you both options. There's the one option to buy in on the front end and get credits, or there's another option to subscribe to the program over 20 years, and maybe that will increase your bill up front. Maybe it'll save you money down below. So they call them solar blocks. And so you get 4 different options. The first option is you could buy one block of solar for $1,200, $1,300. Option 2 is you can buy that same block of solar for $40 a month for 3 years, or $20 a month for 7 years, or $10 a month for 25 years. So what do you get for buying that block of solar? And so basically, you're either paying for it up front or you're financing it. What do you get for that? Well, what you get is a 500 watt block of a solar farm. And so your billing credit is going to be equivalent to whatever that 500 block of solar generated, as if it were on your roof. And so electricity in Michigan is about 15 cents a kilowatt hour. Your billing credit is, whatever your 500 watt block of solar generated. Okay, so $1,200, $1,300 divided by 500 watts. It's like double that divided by 1 kilowatt. And then if you back out the 30% tax credit, that's equivalent to paying $3.60 per watt for installed solar. And so that's kind of interesting. At the time when Michigan was offering this program, installed solar on the roof was going between $3 and $4 a watt. And so, basically what this was enabling the Michigan utility to do is directly compete with solar installers. And they'd say, okay, well, don't put solar on your roof. For the same amount of money, buy solar from us instead, and we'll put it out in the solar farm, and we'll take care of all the array maintenance, and you don't have to worry about maintenance and roof leaks and longevity of the system or anything like that. And that's very interesting because remember, residential solar, it costs a lot more than utility scale solar, which at this time might have been going for $1.50 a watt. And so the utility says, well, look, either way, we're going to be losing this revenue to the solar customer, whether they buy it from us or they buy it from the residential installer. Our competitive advantage is that we can go put the solar array out in a field and install it for $1 to $1.50 a watt, and we can make the profit instead of the residential installer, and we can make a lot more profit than what the residential installer could make. And we already have the golden Rolodex because we have our customer base already, and it's easiest for us to contact them, and they already trust us. People by and large trust their utilities. And so that by offering this community solar program, they can essentially compete with rooftop solar. So paying for it up front, the payback may or may not be very good. How would we calculate that payback? Well, let's say we got offered an installation price of $360 a watt, and then after the federal tax credit, that brings it down to, let's just call it $260 a watt to keep the math easy. And then the price of electricity is 15 cents a kilowatt hour. And so what I would do, and this kind of assumes Michigan has net metering and you're getting retail value for your credit. But we go back to PV watts, and we'll put in Michigan, and we'll do just 1 kilowatt solar array, on the roof, kind of keep everything else the same. So 1 kilowatt of solar produces 1,200 kilowatt hours a year. 1 watt of solar produces 1.27 kilowatt hours a year. There we go. Back to normal. And so what we would say is 15 cents a kilowatt hour times 1 point, let's just call it 3 to keep the math easy, 1.3 kilowatt hours per watt per year. We got that from PV watts. $0.15 a kilowatt hour times 1.3 kilowatt hours per watt per year, that turns out to be roughly 20 cents per watt per year, divided by 20 cents per watt per year. That's a 13-year payback. And so where Michigan is pricing their community solar program is getting the customer around a 13-year payback, and that might be a little bit more than what the same customer would get if they put it on their own roof, but they don't have to do any array maintenance. They don't have to worry about it. So that's a pretty good, I don't know if that's a great economic deal, but compared to doing rooftop solar in Michigan, it's a competitive deal. Then again, if you're the customer who went for the increasing my electric bill by $10 a month for 25 years, $10 a month, again, back to the, well, how much per month does this do? Well, if 1,000 watts does 1.3 kilowatt hours per watt per year, and we divide that by 12, and then we divide that by 2 because they're buying that $10 gets you one 500 watt block. So it's, here in this slide, I carry your significant figures or whatever. $10 a month, it really should be divided by 52 kilowatt hours per month. So here's our kilowatt hours. That comes out to be 18 and a half, 19 cents a kilowatt hour. The current price of electricity in Michigan is 15 cents. And so if you subscribe to the 25-year monthly model, you're increasing your price of electricity by 28%. Albeit you don't need to do it for your entire bill. You could just do it for one 500-watt block so that you're really only increasing your bill by $10 a month, not by 28% of the entire bill. But the point that I'm trying to illustrate here is that they've stumbled upon saying the concept of, well, we can either sell it to the customer up front, and the customer, it's a 25-year agreement, they'll get their payback at year 13, and we're going to make the profit up front. We get the money up front, and the profit we make is the difference between the sales price and what we can install utility scale solar for, and that's a lot better than the sales price between residential solar and what the residential installer can install it for. And so as long as we're pricing our program around the same as what residential solar is priced at, we should be making more money than the residential solar installer. We'll be losing the revenue anyway, so this is the way that we can make more profit than what the residential installer can do. Given our marketing strength and marketing position, that is how we compete with residential solar instead of going out of business. Not a bad line of thinking. At the same time, just like they do over in Minnesota, we can offer a monthly subscription plan that really isn't going to save the customer money, that will make us a profit, that will increase our revenue, that will gain us a customer for the next 25 years under contract, and they're voluntarily pitching in to do local solar work. That's not a bad deal either for the utility. And whether or not it's a good economic deal for the customer, at least until your level of participation in a given market exceeds 2%, or the amount of what voluntary green energy sales are going in for, you should be able to find a fully subscribed program, because it's a better deal for the customer than than the value that they're getting out of their current Green Choice program. This is kind of an obsolete slide, so what's happened is now instead solar lending is more popular than solar leasing. Why I put it in is to show you that there are other options to just owning a solar array or taking out a loan for a solar array. Solar leasing is where someone else owns the solar array ultimately. At the end of 25 years, you no longer own the solar array in all of these community under a solar lease. In all of these community solar programs, at the end of 25 years, you no longer own the solar array. Community solar programs are essentially leases. And so what we're going to do is, we're at the halfway point, so we're going to take a 15-minute break. When we come back, we're going to talk a little bit more about solar leasing versus solar lending. Once we get through that discussion, we'll do a little bit more of solar peaker modeling, and then we'll call it a day. So let's take a 15-minute break. It's about 2 past the half hour. So we're going to pick back up at about 13 till. So you got a couple of minutes after a quarter till. So let's take our 15-minute break. We'll be back at 13 till. All right, we'll be picking back up in just a minute. Okay, so welcome back. When we left the break, what we were positing is that a community solar program functions just like a long-term lease, where the participant is not the end user, not the ultimate owner of the system. They're not depreciating the system. They're not claiming tax credits on the system. Those kind of tax-related issues, as well as the maintenance issues, are left to the lease provider. Now that boils down to ultimately who is responsible for the system. Well, let's look at the definition of operating leases, because there's another lease called a capital lease, and so we really need to understand the differences between the two, because there are certain accounting principles that govern them. And so if we want to create our own operating lease for solar, we are essentially creating our own community solar program based on operating lease principles. You know, there's other ways to structure community solar. You know, somewhat ironically, the Security Exchange Commission has said we don't consider community solar programs to be a security because the participants who participate in them are not doing it for investment purposes. You know, getting your money back, maybe never. Getting your money back maybe at year 20 or 25, depending on if the price of energy increases. Now, even getting your money back at year 13 is not what investors want. There's other rules behind making sure you're not establishing a security that are a little bit harder to hit with community solar, such as putting the end user on the hook for maintenance. You know, so it's not that there aren't other ways to do this, but the simplest way is just to structure your program as a lease. And there is precedent for this. Now, here's a company called Arcadia Power, and they're marketing a community solar program. And I'm not sure if they're, you know, they give you, oh, here's your project. And, you know, one thing that's interesting that they do is they get you to share your digital login to your electric bill so that they can combine it with your the savings from the community solar with your electric bill. So they'll pay your electric bill and credit you the savings. let's I'm not sure which program are they highlighting. I need a zip code for Washington D.C. 2009. So they have they say it's now available and join the wait list. So I think they're hiding a little bit more about their program than they used to. And what they were basically doing is giving you a 7-year lease at a 0% interest rate. So you were essentially lending your money to them for 7 years and getting that money back over a 7-year time frame, and not making any money off the program at all. That's not real exciting. When we want to do community solar programs, we're hopefully trying to make it competitive and not make it a joke. Operating leases can be valuable. There are certain rules you have to abide by. The operating lease is up to, but no greater than 80% of the life of the asset. And so you get companies like Solar City arguing for longer recognized lives of the system. So like a standard solar warranty is 25 years. A standard solar life cycle is modeled to be 25 years. Solar City really wants that standardly recognized life to be something like 40 years so that their solar leases can be for longer terms than just 20 years. So operating leases are for up to but no greater than 80% of the asset life. Otherwise, in the eyes of the IRS, the lease participant rather than the lease provider is the owner if they're leasing the system for greater than 80%. So operating lease, the lease provider is still the owner, and the lease participant is not considered the owner as far as tax provisions come into play. And that could be important to protect your property rights. You don't want the owner just showing up unannounced to inspect the equipment on these offsite principles. You want to make sure that nobody's double claiming the taxes. You want the lease participant to, if you're claiming the tax incentives, you don't want the lease participant to claim the tax incentives. You want to make sure that you can say that you're the owner. The owner is the one who's providing for the insurance and maintenance of the asset. And so if you wanted to structure a community solar program where the participant was the owner, where the participant is claiming the tax credits and depreciation, then they also have to provide the insurance and maintenance. And it might be that you help them with that. What's generally common is you create a group for them to network with each other in so that they can all collectively select an insurance provider, a maintenance provider. But you're not the one providing the insurance and maintenance directly. They're on the hook for selecting that. If you provide them with a maintenance contract, they're allowed to say, no, we want someone else to maintain it, not you, because we're the owner. You can tie the lease agreement to the price of electricity and the use of the equipment via a services agreement. It may be more simple to structure it like a traditional lease where you estimate the value over a 12-month interval and then give them a fixed lease amount. Many of the customers that I see in solar do it because they want to know what their electric bill is going to be like. So you may have more successful participation if you structure your lease as you buy into this solar array and you get this much back a month via a lease payment, or conversely, they don't buy in, but they pay so much a month as a lease payment. It's considered a behind the meter or private electricity sale. In some regions, there are laws against offering electricity sales to the public using the public grid. So, when we're talking about this, we're talking about establishing behind the meter assets and participation. An operating lease can be no money down. One big thing about an operating lease is at the end of the term, not that you have to offer this, but if there is a buyout at the end of the operating lease term, the buyout occurs at fair market value. So you may have heard about a lease where at the end of the lease term, you buy the asset for $1. That's a capital lease. That's not an operating lease. So in an operating lease, the lease provider is the owner. At the end of the term, it's the owner's responsibility to remove it. If there's a sale at the end of the term, it's not for some below market value amount. It's for fair market value. And the reason is the owner can claim depreciation on the asset. And if they fully depreciated the asset and it's worth $0 on the books, they then go sell it for fair market value, and then they have to pay taxes on what they sold it for. If they sold it for $1 and that's below its market value at the time, then they're kind of getting out of some tax payments because they've claimed depreciation on value that that they're then not putting back on the table by selling it for below its market value. A capital lease is the opposite of a operating lease. The capital lease, I think there's more wordsmithing that goes along with this term because it's essentially a loan. A capital lease is up to 100% of the asset life. So if you go beyond 80% of the asset life, you're now into capital lease territory. A capital lease is for 90% or greater of the asset value. So if you're financing 100% of the asset via capital lease, it's more like a loan. If I go take out a loan to buy a house or a car, I'm responsible for the insurance and maintenance. If I take out a capital lease to buy an asset, I'm responsible for the insurance and maintenance. And since I'm the owner, at the end of the lease provider sells it to me for $1, basically to say, hey, we're closing it out. It's yours now. So whether or not you want your community solar project to be a operating lease or capital lease is really a question of taxation. Who's claiming the depreciation? Who's claiming the tax credit? And with that comes responsibilities. Who's paying the insurance? Who's paying the maintenance? And not that you can't throw in maintenance fees and insurance charges, but it's like who's responsible for actually maintaining the insurance policy and buying it? Who's actually responsible for making sure the array gets maintained? So in a utility program, they have this golden Rolodex because they already have all their customers paying their electric bills. So they can go and set up their own community solar program, and customers can buy into the program and they can credit the customer's bill directly. You know, for a time there was a concern that setting up a community solar program was akin to setting up a security, and you would be regulated by the SEC for it. The SEC has since come down and said, well, right now we're not regulating it because we don't consider it to be an investable asset. You know, cryptocurrency has a similar issue. You know, if cryptocurrencies are being used as an investable asset like Bitcoin, they're regulated. You know, if cryptocurrency is used as a token that represents something like like blockchain, they talk about a public ledger. You know, there's a solar blockchain we'll talk about in a minute that represents a ledger of electrical production. You know, no one's buying the data in this ledger as an appreciable asset. It's not regulated by the SEC. People buy Bitcoin as a currency. It's regulated by the SEC. And so utility community solar programs before all this were considered safe because utilities are already regulated by public service commissions, so they can go get rate approvals for creating community solar programs. Do you need to be a utility to structure your own community solar program? No. You know, you can structure it as a series of operating leases. You might want some software for keeping track of array production so that the participants in the community solar program can see how much they've been credited. And one way to do that is to use a blockchain, otherwise known as a cryptocurrency, although they're not quite synonymous terms. You know, why would you use a blockchain? What's the difference between a blockchain and not a blockchain? Well, the main difference is with a utility or your bank, you trust that the utility or the bank is representing the numbers accurately. You trust that when you put $10,000 into the bank and that the bank is going to keep it, and when you want that $10,000, it's going to be there for you. And there's, you know, federal insurance and stuff behind that. You know, similarly with the utility, when you buy into the community solar program and they credit you the production, you're trusting that the numbers are honest. A blockchain is a public ledger or a public database. It's almost like a wallet that you walk around with and you open it up and you show everybody how much money's in your wallet. The difference being if someone sticks their hand in and grabs the money out of it, you can see where it goes. It doesn't necessarily mean you can, you know, punish the hacker that stole your money, but it's an open supply chain, start to finish supply chain. Now, you don't get that with a green choice program. When you buy green energy from a utility, they might tell you what solar farm it comes from. They're not going to tell you which exact wind turbine it comes from. So it becomes a trust issue on if they're double counting the production value. And so there might be some benefit for that process of generating electricity and crediting accounts for people, to have accounts that they can check in on and see what their credits are, even if it's not time yet to make the reconciliation. They might want to check to make sure they're getting credits. And then B, for supply chain, they might want to actually check that, you're not double selling the same solar array on the promise that a bunch of different people are going to get the same credit. With a blockchain being that it's a transparent, open ledger, they're able to see everybody walking around with their open wallets and make sure that nobody's run off with the money. In other words, you want to set up a community solar program, you add a blockchain to it, and that gives your participants a little bit more trust in that they can see the solar arrays registered and trace the credits that they're receiving back to the point of origin. And presumably, if they come across a conflict where two people are trying to claim the same credit, that is something that they can check and assure themselves of. It's not a cure-all. They still have to trust that the blockchain provider is honest. In the news lately, we've seen a story of a cryptocurrency founder who died under mysterious circumstances in a foreign country, known for faking people's deaths. And with that, he took the passwords to access over $100 million in cryptocurrency. The fact that all these people had wallets and addresses where they could see how much cryptocurrency they owned did not matter, that the blockchain manager or provider was not trustworthy. So it's not a complete trustworthy transaction, but it does add transparency to the process. And also, you need some accounting software to track all these transactions anyway, so might as well use a blockchain that is being set up and managed for solar production. In fact, the SolarCoin blockchain is already integrated into one inverter manufacturer, SMA, where just within the online monitoring system of SMA, you can register your solar array to participate in this blockchain and start logging your production. And so what the blockchain does is it allows you to go and create your own software and programming for blockchain administration so that you can reassign the credits, the production credits that go to your account. You can reassign them to automatically transfer into other accounts as a way of automating this system produced this many credits and it's divided up between this many participants in this manner. If you're concerned about violating SEC regulations and you want to keep everybody's individual array asset independent from each other, instead of just selling a 500-watt block or a 1,000-watt block of your commercial solar project, you could put them all on individual string inverters and only sell 10-kilowatt blocks of participation rather than a single panel. That might be you're targeting higher level clientele willing to put, $10,000, $20,000 entry fees into a community solar array rather than trying to sell a single panel. that might lend itself better to corporate sponsorship. You have a commercial solar array on a school building whose individual shares are owned by individual businesses. At that point, the school can't claim the tax credits. You may be in a better benefit for the end user to claim the tax credit, but you want to keep everybody's arrays separated so that you don't form a common pool or a common security. A blockchain software can help you with that record keeping. It's also kind of fun to participate in. Anyone who owns a solar array can go to the Solar Coin Foundation's website, download a wallet, is what they call it, register their solar array, and be credited with Solar Coin. Now, what can you do with a solar coin? Hardly anything. I mean, it's like a coupon where it has 1/20th of a cent cash value. This is like 1/200th or 2,000th of a cent cash value. It's not about the solar coin being worth anything. It's about being able to develop applications that add value on top of it. And so your community solar structure, at its most simplest form, would just be a operating lease structure between the project developer and the community solar participants. There's other ways to structure your project ownership. If you have all the investors in the project up front, maybe you form an S corporation, which is an easy way to divide up the revenue and tax incentives equally among the members in proportion to their level of participation. What an operating lease lets you do is not have all those upfront investors when the array comes out of the ground, but allows you to sign up people after the project has been built. And you can either do an operating lease as a sale leaseback where, they're giving you a lump sum amount of money up front and you're making payments because they're, based on their buy-in. Or they sign a contract where they're guaranteeing to make payments and then you may be crediting them back production on a bill based on how the array performs, which probably would be less than their payment. Similar to the two different kinds of community solar options that we previously discussed. The one where you buy in up front and you get a credit on your bill. The other one where you increase your bill and therefore you're making a series of payments which may or may not be offset by credits, which may or may not have value greater than your payments. Okay, so how do we bring this all back into commercial solar peaker development? Well, for one, let's just look at some solar installation prices between residential solar and commercial solar batteries. Let's say you live in a state such as, Iowa. So Iowa has net metering. So let's assume they're getting 12 cents a kilowatt hour for their electricity. Iowa has pretty good sunlight. So let's assume they're getting 1.4 kilowatt hours per watt per year. Now you take your $2.50 a watt installation price and then you back out the 30% tax credit and then you divide by your kilowatt hour per watt per year price multiplied by your kilowatt hour rate to get your simple payback. And so if you had a net metered rate of 12 cents a kilowatt hour and you had an installation price of $2.50 a watt, you would get a 10.5-year payback. Or if you go further up the Northeast coast, your production goes down, but your electric rate goes up. And so maybe you get a better payback in New York than you do in Iowa. Even though Iowa's sunnier, electricity in New York is more expensive. It's not just about how much electricity you produce. It's also about how much energy you consume. You know, what your energy cost is, how much the value is worth. Well, a commercial solar battery adds cost. You know, your array price goes down, but still you have to buy the battery. However, almost uniformly, you know, yes, it works better the lower your energy rate goes and the higher your demand charge goes. But almost uniformly, your demand charges can give you a better payback. Your commercial demand charges can give you a better payback with a solar battery than you can get with a residential solar array. You know, there's some instances where the residential customer has the option of going on to a demand charge, and usually those residential demand charges are not like what is offered to the commercial demand charges. And so there's been controversy in the industry where the utility has wanted to push residential customers onto demand charges. And I'm not trying to say the solar industry was wrong in opposing those specific instances. You know, instead, what I'm saying is if the residential customer had the same ability to get the rate structure that was being offered to, you know, particularly to commercial large general service customers, they would be able to obtain a quicker payback. Now, the caveat being usually for your large general service, the meter fees are, you know, upwards of $150 a month. And so, you know, that's where, you know, your large general service customers are with high demand charges and low energy rates can get the best payback in the industry. Even if the demand rate is, you know, smaller, the payback is still better than residential. And to some extent, it's site specific. You know, the spikier your load is, the better your payback. There's a balance between a small array and a large array. You know, smaller arrays cost more per watt, but can better target the spikes. Larger arrays, you get economies of scale, but you have to take off more of the mountaintop. And so you get into diminishing returns the wider that mountaintop becomes. So this is where the overlap is. Now, there's lots of residential customers who can't put solar on their rooftop. Those residential customers participate in community solar programs. Most community solar programs offer paybacks that are much longer term than what a typical investor would be interested in. There are community solar programs out there that get voluntary residential participants that don't offer any return at all for the participant. There are other programs where the return on investment comes at year 20 on a 25-year contract that has no residual value. Investors want their money back within 10 years. Usually they want their money back even quicker than that. And so the question is, if I build a commercial solar peaker where I can get that payback under 10 years, what happens when I sell it to another investor who's happy with a 20-year payback instead of a 10-year payback? Well, what that means is I can buy the 10-year payback project, mark it up, and then go sell it to the 20-year payback investor. What that means is if I can take a short-term investor who wants a higher rate of return and then go sell his investment to a longer-term investment seeking a lower rate of return, what it means is I can cash out that early-stage investor with him still making all of his profit, but he doesn't have to hold on to the asset for 6 years or 5 years to get his money back. He can get his money back as soon as the community solar program is fully subscribed. And so what I would posit is that any commercial solar program, any commercial solar peaker that has a reasonable return on investment and project size can be converted into a community solar program and increase the profitability of the project. And that is exactly why utilities do community solar, is because it is profitable for them to do so. They have to do something green, might as well be something that makes a profit. Maybe it's not the cash cow that these voluntary green power programs were, which I think were so profitable they were borderline fraudulent, but it's still something that makes them competitive with residential solar, and it's still something that they find an appetite for as far as participants go. You get some value in participating in a community solar project. The people want to help the environment. They want to do something about climate change. So you give them a solution to do that. Maybe they're not buying in at the $30,000 level it takes to do a solar array or $50,000 level it takes to do an off-grid solar array, but maybe it's just something where they want to spend a little bit of money, have a little bit of mitigation in their electric bill, and get the feel good. Or maybe they're corporate sponsors who are buying in for the advertising principle, but don't want to commit to putting it on their own rooftop. So, a great community solar jobs, site could be a school building if it has the right load profile. So maybe not exactly a school building, maybe a sports stadium, a convention center, something with a little bit spikier load. You take the ideal job site, the ideal customer with the ideal spiky load to get down to the short-term return on investment, and then maybe your community solar participation doesn't have to be a ripoff. Maybe it's something that is competitive. If you can make it more competitive than the utility community solar program, then you really have a product, because then you have some competition that you can say, okay, well, Georgia Power just launched a community solar program, and that's going to increase your bill by 20%, and you're never going to get your money back. But my program, you get your money back at year 13. So this is a study was published way back in 2008. That's when I got into solar. This was one of the studies I read that really encouraged me to jump into the solar market. I think this figure was very important. What it shows is the level of market penetration that an energy technology, not solar, not batteries, not wind, just efficiency would fall into this category too. It says what payback year can you hit in order to get participation? And so, year 15, year 13 payback is way down here at like 2% of the population. And that's where we see community solar participation. Commercial solar peakers, you can usually get an 8-year payback under a right-sized system. In the best cherry-picked markets, 4 years is not out of the question. And so the idea is, develop a solar project with an investor when you can target this payback and then sell it to the community at that payback so that you can then go and repeat your project on another job site, do more solar, drive up renewable energy. If you're particularly cutthroat, if you're targeting the best markets, which are usually rural areas, some of these rural grids only have 5 customers per mile of power line. So if you go and take the best revenue stream off the market, the local cooperative on that market's going to go bankrupt, and then you can come in and take over the whole market in the area doing your solar financing. I mean, the cooperatives are kind of asleep at the wheel in the sense that they have the Rolodex, they have the ability to go get long-term, low-interest financing, and they're not doing this stuff. So, if you want to be an investor activist, this is kind of the best way to do it, is to go into these asleep at the wheel middle America states that have high demand charges and terrible solar policy, wallop them with commercial solar peakers, drive the existing stakeholders out of business because you've taken all their profit centers away, and then expand into less lucrative customer markets, because eventually, someone's going to have to come in and serve the role of the cooperative to provide electricity to everyone else. That's why the cooperatives exist. So it's very important to develop clearly defined, transparent, easy to understand cash flow models of these systems. And luckily, there's software out there to help you do that. So what we're going to do is model our own commercial solar peaker in a spreadsheet. And then we're going to go in and be better able to understand what's going on behind the scenes in your commercially available solar software that makes our spreadsheet model much more accurate and boosts your ability to model these systems. So, this is Energy Toolbase. It'll model internal rate of returns, simple payback, return on investment, net present value, taking into account things like degradation rates, electricity escalators, discount factors on your capital, doing a true post-tax flow analysis. And I think this post-tax flow analysis is where solar installers doing their own economic modeling really mess up. In fact, at the last, I'm in it's not a union. It's like the U.S. Green Building Council, but for the solar industry, or the American Institute of Architects, but for the solar industry. It's called NABCEP, which is NABCEP. They have a nice little installer locator on their website if you need to find. Oh, sorry, I shouldn't have deleted it. It's NABCEP. Let me pull it up real quick. So here's the NABCEP locator. I'm going to just click on a state, Kansas. And here's contact information for a variety of NABCEP installers in the state of Kansas. And click on Mississippi. There's only 2 of us. Not too many. We don't have much of a solar market in Mississippi, but I get most of my project referrals through this website because there's no competition either. You know, in a state like Texas, you know, there's just tons of you know, these are it's a private organization. There's a private test you have to take, you know, show some experience. You know, the NABCEP test has a reputation for being hard. I think that any master electrician with a little bit of solar experience could pass the test without studying for it. So, you know, I have I don't know. I think a good way to prepare for this test is to first prepare to pass the master electrician exam, and then, you know, preparing for the NABCEP exam is not that big a deal. Now, the reason why I mentioned that is because Energy Toolbase went to present a presentation to the NABCEP Continuing Education Conference last year, and a number of installers were pushing back on their cash flow analysis because this is what happens. When you install a solar array that reduces a company's electric bill, well, corporations deduct their electric bill from their taxes. Cost of doing business expense. Now, residentially, you don't get a tax deduction on your electric bill. I wish you did. Residentially, you don't claim depreciation on the equipment you buy. You know, there's no tax deduction for me going out and buying a solar array and putting it on my home. If I were a business and I go buy a solar array and put it on my business, I get to claim depreciation. Now, I often wonder about property taxes and how that relates, because, you know, when you fully depreciate an asset, it has 0 book value. A lot of energy equipment, you know, it's popular for a state to have a property tax exemption for solar equipment at the residential level. I think that's a pretty good policy for making sure we're not treating corporations better than people. On the other hand, when you're a corporation and you lower your electric bill by $4,000 or $5,000, what that means is you're making an additional $4,000 or $5,000. You save $20,000 a year on your electric bill. You're paying taxes on $20,000 a year more in profit. And so that is where depreciation balances out. Depreciation is not a real incentive in the sense that it's a post-tax deduction. And in your post-tax analysis, a business, unlike a residential customer, is paying taxes on their electric bill savings. They're more profitable. They're paying taxes on that higher amount of profit. If I, as a residential household, save $1,000 a year on my electric bill, I do not pay $1,000 more in taxable income. But if I'm a business and I save $20,000 a year on my electric bill, I am $20,000 more profitable. I pay taxes on that. And so where solar installers mess up is they go and do commercial economic modeling like they do residential, and then they add in depreciation, and then they don't add in the tax effect of that you're paying increased taxes because now your electric bill is lower. So it's very important when you're modeling commercial solar to do a proper post-tax analysis, and it's not something that most solar installers will even accept as something they should be modeling, to the point where they're challenging the economic experts on it when they're presenting this information in conference. I'm on the side of Energy Toolbase and saying you got to model the tax effect. If you're modeling depreciation, you can do a pre-tax flow analysis, or you can do a post-tax flow analysis. The main advantage of depreciation in solar is that it's accelerated. You know, there's some special elections to depreciate it all in year one, or absent that, bonus depreciation where you can, or accelerated depreciation where you can accelerate it in 5.5 years instead of 25 or 30. If you're not paying much in federal taxes, there may be a reason to not take the accelerated depreciation and have the tax effect and depreciation effect kind of smooth each other out. Anyway, so all kinds of cash flow analysis that'll make CFO smile can be calculated by Energy Toolbase. Energy Toolbase also does a free trial. You got to give them your credit card to get the free trial, though, so take that in mind. And so how we do kind of our pencil and paper payback analysis is you take the install price, you back out the value of the tax credit, and in solar, we would take the effective generation rate of the array, which might be retail value for net metering. If you don't have net metering, a good way to do it is take 2/3 of your outflow rate and 1/3 of your inflow rate to get your effective generation rate. And take your PV watts number, your effective generation rate, your price divided by your production value will give you your simple payback. So here we're doing an array at $2.60 a watt versus an array at $1.78 a watt. Installation price matters. Now, it's a little bit harder to do this with commercial solar for a couple of reasons. One, one way to do it is you can take your, let's say 1 kilowatt, and it, let's say it costs, let's just keep the math simple. Let's say your commercial solar battery costs $3 a watt installed. We don't have our kilowatt hour rate times our kilowatt hour rate. What we have is a monthly, let's say $20 a kilowatt demand charge. And then we have 12 months of production. So we have 1 kilowatt of load leveling can save us $240. So in other words, 1 watt saves us at 24 cents a watt a year. Whereas if we do a more traditional solar generation rate, 1.4 kilowatt hours per watt per year times an effective generation rate of 11 cents a kilowatt hour, that's going to be, 15.6 cents per watt per year. A right-sized commercial solar array has a higher per watt per year payback rate than a energy rate structure solar array without batteries. A commercial solar battery that's right-sized has an earlier payback than a batteryless solar array, despite the higher cost, because its generation rate is higher. And that becomes especially true when you take out the net metering and you don't have an 11 cent generation rate and your outflow rate is closer to 3 cents. This number goes way down, and commercial solar becomes all the more cost effective, to the point where maybe the only viable solar option in a region is to do a commercial solar battery on top of a commercial job site and have the community participate in that job site, because putting it on their own rooftop without net metering is not cost effective. And lo and behold, that would be the best way for us as a society to be funding and financing solar, because it is putting point of use energy back on where point of use demand is needed, and economies of scale due to the larger installation site and larger electrical consumption can be had. And so, in other words, if we threw out all commercial solar subsidies tomorrow, we would see this correction of putting money back towards the most cost-effective applications. We would see the commercial solar market grow, and there's no reason for us to have to wait for the subsidies to go away to recognize that this is a opportunity. And so again, back to our modeling discussion, we need our interval data for every single period of the year, and then we need our solar production data for every single period of the year. And then that'll give us something that's kind of dumb. Without a battery, we would be outflowing, and then we still have this little peak. So then we need to go and add, a model where we say, okay, I'm going to go for this target threshold of demand. So this is showing me a 70 kilowatt demand. I'm going to aim for a 51 kilowatt threshold. And so whenever my new building demand is above this certain threshold, I'm going to turn on my battery to reduce that threshold. And then if I'm charging my battery with my solar array, I need to make sure that my solar production is equivalent to my battery production. And that's, on a sunny day, that's very easy to do. On a partly cloudy day, that's still pretty easy to do. But on a partly cloudy day, we're running our battery more, our solar array is doing less. And then, of course, on a completely overcast day, maybe my building load is down, but I'm still running my battery. I have to make sure I have enough power from the previous day or two's worth of solar to go in and charge that battery fully. And so eventually the model gets so complicated that you really need to use a computer and more than just a basic spreadsheet to figure it out. What Energy Toolbase is doing here is they're taking your demand charge and load profile and energy rate, and they blend it all together to develop an optimization algorithm that says, look, you have a spiky electric load. So if you try and do a 29 kilowatt load leveling, you're doing pretty good. And that same equivalent savings is true up to a 57 kilowatt load leveling. And it's still pretty true up to an 86 kilowatt load leveling. But if you went all the way to 114 kilowatts, you start to get into this wider, you're no longer in the spike. You're trying to load level the whole mountaintop. And so, maybe 114 kilowatts isn't cost effective for now. Maybe the best thing to do is to stop at 86 kilowatts. And for that matter, that's a lot less controversial because the utility is still getting income. You're not outflowing onto the grid. You're not taking the customer away from the utility. You're just reducing their demand and targeting the most profitable revenue that the utility has. Here's a video link that shows an example for Energy Toolbase. We're just going to hop in and do one ourselves. And here's some links to some free software that allows you to do a little bit more battery modeling and cash flow analysis for solar. I have just found that these softwares are really clunky, and so I would prefer to understand what's going on by developing my own model in Excel or Google Sheets using PV watts and my interval data. And then if I'm doing this professionally, hop into Energy Toolbase. Okay. So what I'm going to do is I've gone ahead and prepared this spreadsheet. I think I can share it. Let me see how I do that. Let's see here. I actually don't know what happens if you click this. I don't know. If you can edit the document, please don't. Maybe I need to make a copy right after class. But here we have on the left, let me make this a little bit larger. Here we have on the left the interval data that I get from the utility. And so one thing to look out for is the interval data will often have a multiplier associated with it. So in this case, the multiplier is 40. And so they're scaling up the building demand to get from point A to point B. And so you got to just make sure that you're converting the interval data that you're downloading. You have to take a look at it and make sure it reflects what they're billing you for to figure out what that multiplier is. And so here we have our old building demand that's measured in kilowatts. And see at night it's at 4 kilowatts. And then in the morning, right at 5:30 a.m., 5:45 a.m., it spikes to 55 kilowatts, 88 kilowatts, 89 kilowatts, 89 kilowatts. And then, around 8 a.m., it's at 68. And then by 9:15, we're back down to 30 kilowatts, and then substantially less for the rest of the day. Then maybe a little bit more in the evening. More and more people start entering and exiting the building, and the heaters click back on momentarily. This is at 2:30. Another spike in the evening. And then at midnight, we drop back down to our kind of base load. And what we have is that for every single 15-minute interval for the entire day. So yesterday, we went to PV Watts, and we ran our PV Watts simulation. And what we did is we downloaded the hourly data from PV Watts, and we ran into this problem. And the three problems that we're going to run into is that PV Watts looks like the form timed out, didn't give me my data this time around, but that's really neither here nor there. PV Watts is going to give us hourly data. And then we also need to check for leap year. And we also need to check for daylight savings time. And so if you end up having a blank day or a blank hour in your data set because of leap year or daylight savings time, just use the previous day or the previous hour and kind of smooth out that data so that it's all consistent. So leap day, daylight savings time. And then there's the fact that PV Watts is done on an hourly basis, and your interval data is usually done on a 15-minute basis. It might be done on a 30-minute basis. So it's like, well, how do you get your hourly data to match up with your PV Watts data? And so for that, we just copy and paste our PV Watts data 4 times and then sort it by the month, the day, and the hour so that we get, this is the sheet that we did yesterday, so that we get, and what we're doing is we're assuming that the solar array output is consistent and flat for each of those 15-minute intervals for the hour. And so, in other words, at high noon on January 1st at high noon, PV Watts was telling us that our solar array, our system output in watts, let's do here I'm doing it for a 1 kilowatt array, but remember, remember that when I did this PV watts calculation, I downloaded as a 1 kilowatt array so I could create a scalar. And so I'll actually have a little cell here where I can just make it a 100 kilowatt array or a 50 kilowatt array and have my array size kind of jump around on me. And so right now what we're seeing is that for our 100 kilowatt solar array at high noon, our array is outputting 15 kilowatts. And so what we're assuming is that it's outputting 15 kilowatts for the first 15 minutes, same thing with the second 15 minutes, same thing with the third 15 minutes, same thing with the fourth 15 minutes, and then it jumps to, the next 15-minute, the next hour interval, which we've replicated 4 times over to get us our 15-minute interval data. And so you kind of have to riddle your spreadsheet a little bit to make sure that your interval data and your PV watts data are the same. But once you have that, so here I have my old building demand, and then here I have my array size, and I can toggle it around however I see fit. And that gives me my new building demand with my solar array added to it by basically subtracting the two from each other. And so I have up in here, I have column F minus column H. Okay, well that's without the battery. So what we need to do then is have a demand target that says, okay, well, if my building demand with solar is greater than this target, turn on the battery and do load leveling. And so I have a little formula in here that says, if this column is greater than this column, turn on the battery and make it this column. So now we're running our battery, but this is assuming that our battery right now has an infinite size, and obviously our battery doesn't have an infinite size. So the next column we need is a battery bank size. And this is yet another guess. We don't know what it's going to be so far. The way that we guess this is we go and we look at our, all the columns. We take our battery capacity and we guess that it starts at 100. Okay. So we're starting at 100 kilowatt hours. And then our new building demand after our battery is 4 kilowatts. And we don't care about that because we're only running the battery if it goes up above 51. And so we have our column here, and then all of a sudden we're on January at 5:30 a.m. when we saw that load spike, and our load is up to 55 kilowatts. And so we say, okay, well, we need to run our battery to keep our load at 51 kilowatts. And what that means is we're drawing power out of our battery. Same thing for the next hour. Same thing for the next hour. Same thing for the next hour. And what we see is our battery load level starting to deplete. And it keeps going down and going down and going down. Well, what's happened at this point let's see if I can. How do I do this? I learned this recently. Freeze up to row 3. There we go. So what we see is finally the sun comes up around 9 or 10, and our solar array starts turning on. in power, and it's not a huge amount of power, but our building demand, isn't, basically what's happening at this time is, either our battery's not being used, or eventually the solar array is exceeding the battery demand, and we're starting to add energy back in to that battery. Of course, we're saying our battery is only a 100 kilowatt hour battery, so once it gets above 100 kilowatt hours, we have to make sure it doesn't exceed our maximum battery size. And so through formula linking, a lot of if formulas within our spreadsheet, if the battery capacity is greater than the maximum battery size, make the formula the maximum battery size. Don't, overcharge our battery with capacity it doesn't have. So now our solar array is healthy. Our building demand it's nighttime. It's back below the threshold. Our battery's at a full state of charge. And then we're on to the next day, where either the next day, our solar array comes up, and our solar array may actually be outflowing to the grid, and our battery's at a healthy state of charge. And so what I've done here is to say, well, is our guess good enough? Is 100 kilowatt hours all we need for this battery to be healthy? And so I can do that by just scanning this whole column's data set and saying, what is my minimum battery level? And so that's 58. So what I might have to say is, well, how would this change if I had 150 kilowatt hours in my battery instead of 100? Well, it actually didn't change too much. Oh, there's so much data in this spreadsheet that I have to be a little bit more patient than I normally am. So here we are at 150 kilowatt hours, and our battery bank is now going to be at -8. And so I have to say, okay, well, not to fully deplete my battery, at that point I need to have a 158 kilowatt hour battery to make sure this doesn't go negative. Alternately, I could increase my array size and see if that matters. Now, you have to do both, but your battery size is what's going to get you out of the negative, and then the array size may hedge that from there, because normally when your battery bank is going negative, it's because you're going through multiple days in a row where there's not sunshine. And solar will actually produce energy on a cloudy day. It just matters how thick the clouds are. So there is a little bit of a balancing act to say how advantageous is it to add more to your solar array instead of increasing your battery size. And basically you have to find that balance through a iterative guess and check process. And so what I've done here is in the first iteration, we're setting a demand target of 51 kilowatts and kind of honing in on our best payback. Except at that point, I'm saying, okay, well, we only need to be above 51 kilowatts for 1 month of the year in order to stay in that demand charge. And so I'm looking at each load, and then instead I've gone and created a different demand target for every month of the year and try to see how low can I level the demand to still not have my battery bank go negative, and try and pick the best month of the year. So February, I have the highest demand. That's when I'm load leveling to just above 50 kilowatts. And then every other month, I'm pushing it, or December as well. So it's not just the maximum demand, but in December, I have high demand and fewer days of sunshine than in February. And so, you might not be able to. So it's like in December, I can go down to 65 kilowatts. That's above my 51 kilowatt target. But you might find that to go all the way to 51 kilowatts, you get into diminishing returns. So what we have further down the spreadsheet is a cost associated with my battery bank size and a cost associated with my solar array, so that when I go and toggle my battery bank size and my solar array size, it impacts my economic model here. And so, through an iterative process, examining the demand charges for every single month, examining the solar array production for every single day, associating that with an installed cost of the battery bank and the solar array, I can hone in through modeling on the most cost-effective design, which is what led me to a 122 kilowatt-hour battery bank with a 14 kilowatt solar array, and saying, you know what, I'm not going to try and demand load level any further in December, because to do that, I'd have to increase my battery bank size even further. So to kind of load level in December, right now I have a 5-year payback. To load level in December down to 51 kilowatts, I need 174 more kilowatt hours in my battery bank. And so I could try to go back into my model and make it a 22 kilowatt solar array or a 50 kilowatt solar array, and go and make my battery bank maybe 160 kilowatt hours, so that I could hit that load leveling. But what we'll see in our model is that this payback year is going to jump up because we've increased the size of our solar array and our battery bank. So real quick, it's really not the role of continuing education to highlight commercial data. But what we're doing on a spreadsheet not only does Energy Toolbase integrate financing into it, so you can model, what the array looks like on a 7-year term or a 20-year term, and determine the interest rates associated with that. But here is kind of what it looks like in a commercial setting, where we're modeling our federal tax rates, the discount factor on our money, the escalator, and the overall cost of electricity. One thing that the commercial companies do very well is model and program the utility rates across the country, so that sometimes it's advantageous to select a couple of utility rates and compare them. Is it better to be on large general demand, or do enough load leveling to knock yourself into small general demand? Hey, Joseph, you'll get a quiz. Yeah, it's over at 3:15. You'll get a quiz link in an hour, so if you have to hop out real quick, it'll show up in your email address. You can model incentives like depreciation and the tax credit and any local incentives. It crunches the numbers for you. But really what I wanted to show you is their visualizer, where you can go in and hone in and say, okay, well, this is my solar production, battery usage, and whatever for the whole month of January. And so what I'm going to do is I can see that this is the first, second, third, fourth, fifth, sixth, seventh, the 8th day of January here. So I'm going to go and zoom in on the whole week and then kind of go over and say, okay, here is my maximum demand after I do load leveling, and so what's going on this day. And so I can see in this red line here, my battery's at its full state of charge. This is the weekend. Don't need to use it over the weekend. I'm outflowing onto the grid. And then here, my battery is turning on as my demand spikes. And so I'm going all the way down to 0 state of charge, or a 20% state of charge. So I have it throttled to reserve 20% left in the battery. And it gets to the bottom and it can no longer do load leveling. And so that's just enough for my solar array to turn on. So I got kind of lucky there. And so then I go back and I look at this and I say, okay, well, I'm looking at my new load profile right here in light blue. And what I'm seeing is that here in light blue, it's kind of a plateau. And so I am getting into that diminishing returns where I have this other base plateau and then my off-peak plateau. And like this is as far as I can do for load leveling. If I went any further, I might as well take the whole building off grid. And now I'm kind of halfway or more than halfway between the top of my peak and my, normal operating plateau. And basically, when you get about halfway down that spiky peak, you're already past your point of diminishing returns. And so the point is, by visualizing the data, your battery state of charge, your spiky versus your plateau peaks, you can develop a narrative to understand what's going on in your array, and that'll aid your ability to say, okay, well, should I start off with a larger battery bank or a larger solar array? Well, what I can see here is that my solar array is really not doing anything until about halfway into that plateau. And so, I'm at the point where to do further demand management, I would need to increase the size of my battery bank. I would need to be load leveling a plateau instead of a spiky peak. And so I'm at my point of maximum return. I don't need to do any more modeling on that. Okay, so with that, we are at the end of the program. This is just kind of saying, hey, don't forget that in these valleys between your maximum demand charge, that is the cheapest electricity in the United States. So if you are into Bitcoin mining for profit, that's another way to make your commercial electricity interconnection more profitable, is not just by shaving off the peaks, but then by filling in the valleys. Bitcoin mining being nothing but converting electricity into money. You have to have a cheap electric rate to do that. That's a great use of this. And so eventually what you do is control your electric demand so that you can make your load profile into a perfect, long, flat rectangle, such that instead of the power company optimizing the rate structure to punish you. You are optimizing the rate structure for maximum profitability. All right, so that's the end of the program. If you want to email me for course updates, video recordings, I make video recordings. I'm happy to give them out for further reference. Feel free to send me an email. It's jrskromer@gmail.com. Or you can contact me. My website is www.community.solar. So with that, thank you, and I'll pass it back to Half Moon.
All right, thanks, John, and thanks everybody for attending this afternoon. A reminder, if you're taking today's quiz for continuing education credits, or excuse me, if you're taking today's course for continuing education credits, please remember to take the quiz, which will appear shortly on your screen. Once we receive that back, we'll then be able to send your certificate of completion to you in your email. Please allow approximately 5 business days for us to process your results. If you do need your certificate sooner, just give our office a call at 715-835-5900. If you can't take that right now, you will be able to access it later in a follow-up email that will be sent in about an hour. I'd just like to thank everybody for attending. Thank you, John, again, and everybody have a great afternoon.